All right, so welcome back everybody for today's session of the Cardiff Analysis Seminar in online format today. We are delighted to have Dimitrios Tsagkarogiannis from the University of L'Aquila, who will talk about density functional for inhomogeneous systems. So thank you very much for accepting our invitation, and over to you.
Yes, thank you very much, Matteo. It's a great pleasure to be with you today, and it's a great pleasure to give this talk to your nice department. Actually, I went through the interests of the members, and I hope that I will present something which you might find interesting and relevant also to your studies. Okay, so this is a joint work with two collaborators, so Sabine Jansen, who is in Munich, and Tobias Kuna, who recently moved to L'Aquila as well. So partly it's a UK product because this collaboration started when all of us were in the UK. So me and Sabine, we were in Sussex and for a year together, and Tobias Kuna was in Reading and we were traveling often. So it's a long-term collaboration which goes on, and I will try to give you an overlook today. And so the plan is the following. So I will try to give an introduction about what are the main techniques in statistical mechanics to compute free energy functions. And I will give you two examples on which I will structure my presentation. A simple one, which is the homogeneous case, and this paper is about, this work is about the inhomogeneous case, which is particularly interesting in a series of applications, inhomogeneous. In particular, we were inspired by liquid crystals, and I will focus on that as I go on, but it can be generalized in other scenarios. And the goal of my talk is to say what is special in the inhomogeneous case, what are the mathematical difficulties, what are the challenges, and present that based on some simple calculations, maybe from the homogeneous one, which I can do in a seminar of 50 minutes. Okay. So then the main tools are two. So the first one is the large deviations principle. So the large deviations principle. And I will try to put it in a general context, which has been already studied. I mean, you can actually find it in books, and see what is new here. And the second technique is when you do the large deviation principle, you arrive with a variational problem. So in some cases, you can solve explicitly this variational problem by expanding the solution in a power series. So this is very much related to another technique from statistical mechanics called the cluster expansion. So compute the variational principle from large deviations using cluster expansions. And I will comment on the validity of this and the limitations and all. Then I will try somehow to be more precise about the importance of the inhomogeneous systems. And a key point in this analysis is an inversion formula. So, key technical tool is an inversion formula which appears while I try to compute the supremum of the variational principle. And there are some combinatorial issues related to. And then I will conclude with some conclusion. Okay. So I have planned it like 10 minutes each one of these. So let's see what I will manage to do. Okay. So what is the goal? So the goal is if I give you given an order parameter, so given G a density, which is a function, could be of space, could be of orientation in some function of space. So in some function of space, in some domain. No, I mean, we will see. Compute the free energy which is a functional of these functions, and it is given maybe by density function f0 of rho x dx, but it might be more complicated. It might have 2-point correlations, so it can be a general function. So compute that starting from microscopic system. Okay, so this is the goal, and we are in classical systems. No quantum effects will be relevant here, and we are talking about equilibrium. We will not talk about PDEs. Of course, once you have the equilibrium theory, you can think gradient flows and things like that and write the relevant PDE. But here we are talking only about functions. So 2 examples, as I said. So I present the homogeneous one because notation is very simple. I would be unable to do the inhomogeneous one in a Blackboard talk of 1 hour. So but I will say what is the difference. So homogeneous is what? So I have a box lambda in RD, and let's say I have particles of on the position. So I have x1, xn particles, and these interact with each other, and they have some energy which depends on the configuration x. So x is x1 xn, and okay, maybe I will not be very consistent with the notation. Please feel free if something doesn't fit well, so that I comment on that. Maybe going fast, I make mistakes. And let's say it's a pair potential. No, so there is every 2 particles, I and j, they interact with each other with a pair potential. So the Hamiltonian, the total energy will be the sum of a potential V, which might depend on xi and j, and maybe depends on their distance. Or it could be even more general, so it might only depend on both, not necessarily by the distance. So in full generality, let me write like this. So this is the energy of the system, but since now we are in a microscopic scale, so the fluctuations are important. So the theory of statistical mechanics found a way in order to describe that. And this is given by the partition function. So this is a function of lambda, and n, which is defined as the integral over all configurations, so over all positions x1, xn, lambda n, of the weight of each configuration, which is given by the exponential to the minus the free energy, and there is a parameter in front. So this essentially says that configurations with high energy are less probable. So it's e to the minus a big number. So they contribute less than configurations with less, smaller energy. And I need to integrate over all possible positions of these contributions. And this is called the partition function, which is very important for the macroscopic properties of the material that we described of the system. Okay. So all the information is registered in this number. This is a number. I need to integrate. Now for each lambda and each n, capital N, this gives me a number. I just integrate over the position x1, xn of this exponential. It looks trivial in some sense. And there is also then factorial because these are indistinguishable particles. So if I change the labels of them, I get the same thing. So I'm overcounting many situations, and I'm overcounting n factorial many because by exchange of labels, by the permutations which are n factorial, I get the same thing. So I need to normalize with this n factorial. So all the microscopic information is registered in this number. Now, I don't want to do the theory of statistical mechanics. I guess most of you have some minimal exposure on that, but this is what we need to complete. It might seem very naive. You would say, okay, it's an integral. We know how to do it, but it's very singular, and it is very difficult to compute it by hand. Because as you see already, h lambda, so if I write, so this is e to the minus, there is a sum here, which correlates the particles. And these integrals are non-dependent, so I mean, it's not just a product of integrals. There are ways on how to compute. Okay, so this is the so-called canonical partition function because you fix the number of particles. And there is another, the grand canonical partition function, which you introduce a control parameter, z, which is the activity, and is the sum over all possible number of particles. So it's just adding a Lagrange multiplier if you want, this is z, and I sum the canonical one, where now, before I had the control parameter, which was the number of particles, now the control parameter is the activity, which is just a question. Okay. These are sometimes two equivalent ways of studying the problem, and these are the quantities which in the limit will give me the free energy. In fact, if I consider the density, which would be the number of particles divided by the volume, let's say this goes to a value rho, no? So in this limit, and in the limit as lambda goes to infinity, the volume becomes infinite, the number of particles goes infinite, in such a way that the ratio goes to the density. The free energy for the homogeneous case, where the density rho is constant, is a real number, not a function, is a real number. It is exactly defined as the above limit of 1 over lambda of the logarithm of this. Okay. So this is what one has to compute in order to calculate the free. And now the question, of course, is for the inhomogeneous systems, how to compute the same thing, but for now a function which is not constant. So I need to put myself into a case where, you know, like the average here, the quantity I'm looking is not just the average of particles, number n divided by lambda, but it is something that varies in space. And I need to do that in a proper way. Okay.
Sorry, in the limit that you wrote, you take the limit of lambda and n to infinity in a particular way, depending on the dimension, or?
It's this limit here. And I put this limit here, and I don't take it. Once this is satisfied, I can work. I don't need more special way of taking it. Okay, this is exactly what it is. So yes, I can take dyadic sequences. I can find many ways on how to perform it. And the important thing is that the estimates I'm doing in this technique are uniform in lambda and in n. So I'm quite flexible on how to perform. Okay. Okay. So what is important in the inhomogeneous case? And in order to fix ideas, I only will focus on the liquid crystals because in order to have a specific example. I mean, at the end, I will not even do that. I will be talking only about the general scale. But what is different in the liquid crystals is that now I not only have a position, but I also have an orientation. So my particles have a position xi, which is in lambda, and they have an orientation in some sphere if you want. So let's take it compact for simplicity. So you can think there's two spheres. My orientation, and I can also take modulo the opposite direction. So I only take the line. So I can write the same things as in the homogeneous case. And I mean, this is an old paper, if you want, by Onzager in 49, who went through exactly this program. And with the technology available by that time, he did an excellent work. And this work somehow comes and puts with a new knowledge what Onzager did by that time. And okay, so what changes here? So maybe I just write one formula. I write now the grand canonical partition function that I had before. It will depend. So I can always have an external control Vz. But now the fact that I vary the orientation, I need a function. Now, before I had rho, which was the number of particles, and I was controlling that with z. But now rho is a function, so I need a control which is again a function in order to allow me to control the variations of the profile of the density. And this function, I call it as an external field, is a function p external, which is a function from my space, whatever my space is, 0, 1, b times s into. Right, so I'm having 0, 1, b, the space of the particles, and s is the orientation. So the grand canonical partition function is exactly what I had before with the additional control. So I also have a control over the total number of particles. So I keep the z, and on top of that I put the function. So it will be e to the minus the Hamiltonian I had before. So it will be besides the xi xj, and then I also add the external, which is on xi and on si, and I integrate over all x and all s. Okay, so this is the inhomogeneous. Okay. So the important thing is the scaling. So, and here there are, this is one of the key points of this book. So what is the scaling? So let's try to see how things go. So I am in 0, 1. Let me do dimension 1, no, because I cannot draw it general. So my domain is 0, 1. And I'm fixing a density. So the density is an L infinity function. So it could have jumps, no? So it could be something like that. Maybe, and we have to see in what space we should define. But it in general is a measurable function. It could be even a measure, no? In order to address more general situations. And this is the macroscopic picture. Macroscopic picture. So I have a macroscopic point R, and at that macroscopic point R, I have the value ρ1. So from the microscopic point of view, this means that at each point R, the system has been thermalized, has reached a thermal equilibrium, and it is the result of interaction of a lot of particles that give rise to this macroscopic value of the density ρ1. So if I want to view it from a microscopic point of view, no, so I might magnify with L, so 1 becomes L, L will go to infinity, is the size of the box. The macroscopic point R becomes RL, and if I take a neighborhood of order 1, if I take a neighborhood of order 1, so it doesn't scale with L, I should see more or less a constant value ρ1. Okay, so here I'm putting separation of scales. So this is a mathematical way of addressing the problem, separation of scales. So if you go to physics papers, they don't do the separation of scales. So they think of a box L again, and they ask to observe in a neighborhood RL a varying profile. And hopefully I will comment on that when I arrive to the technical point and explain why I can do the first and I cannot do the second. Okay? Since the interest of many of you in homogenization, I was trying, while I was preparing this seminar, to see what would be the case with the homogenization. So I think one might be able to see some periodicity here and find an intermediate thing between these two. And I will try to comment when I have the formula. Okay. So I put it with question mark because it's something that I want to study. And it is not clear to me yet how to do it. Okay. All right. Okay, so now we go to large deviation. So how do we usually study this? So we need an empirical measure, So the empirical measure is the quantity of interest. So for example, if I need the density, which carries the microscopic information to the macroscopic scale. So it would be a measure which is indexed by the volume, the size of the box, and it has a given configuration. So maybe by eta, now I call x1 s1, xn sn, or even if you want, I can take also the product space, no, for all n of these things, depending on which space I am, but I don't want now to waste time on the technical part. So the empirical density is what? is the sum of the Dirac mass on the position and the orientation. So in this first case, I have to rescale the position, the microscopic position, by this capital L, while the orientation, I have it unscaled. And this is of the order of the particles, capital N, so I need to scale that with the volume. So I divide with the number of volume. So if I integrate this nu over my whole space, I will get the density. Okay. So what I said before about the physics papers, they use this empirical measure without the scale. Okay. And I will tell you why I cannot do that. And somehow one of our interests with my collaborators was somehow to bridge these two approaches and try to see what is rigorous, what is important, and try to see what one can do mathematically. Okay, so we have this empirical measure, and there is a general theory of large deviations in topological vector basis. So, I mean, in some books, for example, you can open Tempo Zeitouni, and you will see it as abstract Gärtner-Elf theorem, but it's just an example. So, for example, if you look at the Tempo Zeitouni, and in this general case, I will give it now. It is written by Baldi. And it's what, I mean, it's what you do in the real life, essentially. So how do we treat that? There is an important quantity, which is, as I said, the grand canonical function, the grand canonical partition function. So in probability, the grand canonical partition function, we call it log generating function. So we have, we usually use the letter lambda, which is the logarithm of the expected value of E to the empirical measure that I define above. So all the information about my microscopic system is registered in this function. And all the properties I need, I mean, if you think in the old, maybe Russian school, is registered in the analyticity properties of this function, whether it has a derivative at 0 and things like that. So this will be relevant. So this is the moment generating function, which is, so the expected value is with respect to the probability measure PL that is associated, if you want, with the grand canonical partition function I had before. No, so I have the grand canonical partition function here. I can write the corresponding probability measure. So the probability of A will be the integral over A, no, of this object. This is how you compute the probability. Okay. So you integrate not over the whole space. So here was over the whole space. It was 0, 0, 1 to the D cross S and the whole thing to the power n. So if I give you a set A of configurations, I integrate over this set A. So the large deviation principle says that the probability, this probability of my measure mu L being in some set A, right? It is asymptotically equivalent with the minus infimum, so actually the log of this, and it has to be normalized by the volume. The minus infimum, a functional, which is the dual of this log moment generating function. So where lambda bar of phi is the lim sup, because this is for lambda of lambda and phi, and lambda bar star now on the dual space of measures, it will be the Legendre transform of phi nu minus lambda bar. So I take nu in the space of measures, sign measures. And since I want to work in the topological vector space, I have to take this dual, which is the continuous bounded function. So the supremum would be over these continuous bounded functions. And if you want, this is the theorem. The only thing one has to check is compactness, so the tightness of these measures, and under some hypotheses, you can prove that. Hypothesis on the potential, on the parameters of the problem. You can prove that, and you can use general theorems, and you get it. Of course, now the point is what is lambda bar star, because somehow this will be your free energy functional, but you have it in a variation principle. It's given as a supremum, and in principle you don't know how to compute it. Okay. So, and this brings me to the third point. So, slide.
Right. Can you just show again the energy, with the spins? How the energy,
sorry.
The energy, how it looks like with the spins, the potential.
Ah, yes, thank you. I forgot to say that. Yeah, you're right. I talked about liquid crystals. I didn't say the most important thing. So if I am here, so the potential V I have has two inputs, has the positions and has the orientations. So for the positions, I can do a big class of things. For example, I can do Lennard-Jones, I can do hard spheres. On Zager, in this paper with the orientations, he did excluded volume for the cylinders. So he constructed cylinders, long cylinders in the direction of the spin point, and he did the excluded volume between two cylinders. So if I give you xi and xj with the orientations si, sj, the potential V is the excluded volume of these two cylinders. Okay.
Okay. So this potential V is more complicated than what it appears.
It is a complicated way. I cannot
it depends on the SI and the SJ
exactly.
as well.
It would take some time to write it explicitly.
Okay.
Only for the positions I can write it, because the xi xj would be 0 or plus infinity if they are close, so it would be 0 if they are far, and plus infinity if they are close within a distance. Okay, but if I put also the orientations, I use that too. And actually, this is an amazing paper where he did in the appendix the calculation of the excluded volume of the cylinders, and it's an interesting calculation, so a non-trivial one. So he did that explicitly, and this is the beauty of these old papers. Okay, thank you very much. So for this comment. So I go fast. So how to compute the sup? And now this theorem is true in a generality, so it is true also within phase transitions and general cases. Now, in the particular case, if we are in a one-phase regime, so I will comment on that. I don't pass it now, but I just want to say that in this particular case, in the particular case, which is actually the less interesting case, but this is what one can do rigorously, the particular case of one-phase regime, one can use cluster expansions to compute the supremum as a uniformly convergent power series. So, which is a technique which comes from mathematical physics, a very well developed technique, and here, I mean, we show how it combines with the large deviations setup. So for the homogeneous case, there is a paper by Giuseppe Scola, who was a student of mine here in L'Aquila. So it was in his PhD thesis at GSSI in 2001, so very recent. And with my collaborators, we did it, Jansen, Kuna, etc. We did it for the inhomogeneous, and this is in preparation, you know, so in preparation. And this is what I'm talking about. So what is the idea? Very briefly, I want to do it in the homogeneous because it is possible to do it. And then I will comment in the homogeneous. And I always look at the time so that I finish by 50. So what is it? So what is the idea? So I have this grand canonical partition function. I write in terms of the large deviations, in terms of the moment generated function, which you can write it in this form. So it is the sum, and bigger or equal than 0, z to the n, and factorial. And here, what do I have? I have e to the minus b, no? So you remember, I have e to the minus sum I smaller than jd. So the trick of the cluster expansion, which goes back to Mayer in the 1940s, is you bring the sum as a product in front, and you add and subtract 1. So this is, you bring the sum as a product, and you add and subtract 1, e to the minus b ij. Let me write it this for velocity, and you add and subtract 1. And of course, I also have the one body potential, which is the external field, but I can put it in the prior measure. So I have the product 1 to n, and maybe let me just write for x, right? Because we are in the homogeneous case to make the formulas simple. So I can put in the homogeneous. Now, the point is that I can develop this product, and this can be written as a series of graphs. So if you develop, so if I call this Fij, I have the product of 1 plus Fij, which will give me, if I expand that, it will give me 1. And then I will take all the ones with 1 Fij, then I will take all the ones with 2 Fijs. And it is not difficult to discover that this is 1-to-1 with the sum over all graphs on n vertices of the product of ij are the links of Fij, and they don't write the measure. The measure is the product measure. So this gave me this. So you see, I will get one graph, it will be just the dots. Then another graph will be, I have the link Fij. Then another graph would be the link Fij, Fi prime, J prime. So you can bookkeep all the terms in this expansion in terms of graphs, and you write it like this. Now, this is nice because since I need to compute the log, it's a very easy combinatorial identity to see that this, first of all, in combinatorics, this is called the generating function of the species of graphs, not necessarily connected. So some G in Gn of the weight of G. The weight of G is going to be essentially the integral of the product of ij's, where ij's are in the edges of the graph G. And this is the generating function of the species of graphs. And this is equal to the exponential of the generating function of the species of the connected graphs. It's easy because if you think the exponential is a partition, the Taylor expansion of the exponential is a partition. No? So if you think in multivariable calculus and try to write the Taylor expansion of exponential of e to the x1 plus x2, you will take all combinations of x1 and x2, right? It's a partition. And this is exactly what this formula is. So, and this is good because the log cancels with exponential and they have a function. Properly scaled with L to the D. So this is how this cluster expansion is performing. Of course, the key point here is it has to be convergent. And it is convergent only in special cases. I don't have time now to comment on it. I should somehow come to the conclusion and maybe spend 5 minutes to the remind. So the point is that here you can write that. And moreover, you can compute the supremum. Because if you remember, now I have the supremum. So in one dimension, it will be log z times rho. So this log z is the z, I mean, is this one, because here phi will be log z, because it depends if you put it in the exponent. So phi is in the exponent, z is down. So phi is like log z, no? Because e to the phi is e to the log z is z, because z is downstairs. Minus what I had here, no, lambda bar of phi, which is now lambda bar of z. So if I want to compute the supremum, I just take the derivative if I am in the real line. If I am in the inhomogeneous case, I have to do it in the right functional space. And here is where the whole trouble comes for the inhomogeneous case. And so if I take the supremum, the derivative will be 1 over z rho equals lambda bar prime of z. And this will tell that the supremum occurs here. So I would need to invert this and find a function and plug it back and obtain lambda bar star of rho. So this was what I had knew before, but in the homogeneous case, I don't need the measured space. I just do it on real line. So it is just a constant, it's a real number. So I write it, and this is the rho, the density rho here, which is evaluated at the supremum. So let's say the supremum is at this function z star times rho minus lambda bar of z star. And here there is another combinatorial identity. So this will be log z star times yeah, I need this formula. I need to compute this formula here. And I can't get an explicit form of, so where f is the free energy. So there is a combinatorial identity because I mean, again, by combinatorics, there is a formula. And the formula one has is given by B of rho, where B of rho is the generating function of two connected graphs. So what are the two connected graphs? So you remember, no, initially on the partition function, we started with graphs. So this was the sum of G in these GNs. And we said that this is equal to the exponential of the generating function on connected graphs. We're now connected graphs, so we went from the general graph to connected graphs. So they cannot be split in connected components. And what happens is that when you do the Legendre transform, the free energy is given in two connected graphs, where two connected graphs are graphs where I can go from one point to another point in two different ways. So, which is kind of nice because you see how you go from one combinatorial species to another by passing through these graph structures. So, if you want me to repeat, we have the log generating function, which was written as the log of graphs. It became the exponential of connected graphs. So this is the generating function of connected graphs. And the supremum of that, when I plugged it in here, gave me the free energy, which is the two connected graphs. Of course, again, we have to discuss about the convergence, and all the work is there. But I just wanted to give you a panoramic view of what happened. So this is how one would do it in the homogeneous case. And it's exactly parallel in the inhomogeneous one, modulo the technical points. And since I have 3 minutes and maybe Matteo gives me another 2, I will conclude with the remarks because things never go as we plan it. And maybe say what are the key technical points in the remarks, which essentially should have been the main. So the first one is that we need a convergence condition, which is quite restrictive, because the convergence condition looks like something which depends a C bar times E so let me see, E to the B, rho anything to norm being smaller a constant E to the minus. So what are these B and C? So C bar is the integral of 1 minus E to the minus absolute value of B integrated over X, B of X integrated by X. And B is somehow the lower bound. Is, for example, your potential B is something like this. B is this constant there. So the convergence condition asks something about the potential and asks something about the regime which is registered in this draw. So in what I was doing initially, know that I have a macroscopic rho that makes jumps, I cannot do it for large values of rho. Rho has to be an infinite. And actually the interesting part of the rho starts above the bound here. So where here values of rho here is where the phase transition occurs, and it's exactly where this technique does not work. Of course, in the old Gonzaga paper, he did exactly this machinery. He found free energy, which is, its validity is not true in the phase transition, but with that function, he studied the phase transitions between the smectic, etc. phases. So it might work, but we cannot prove it. So this is the first comment about the convergence condition. So there are several works about improving by a little bit or more, depending on the inversion technique, and but I don't have time to discuss it. Another interesting point is the inversion. So the inversion in infinite dimensional spaces as we need to do it in the homogeneous case. And this is a joint paper with Jansen, Kuna, and me in 19, which is for some reason again it's 3. And of course, you can find it in the Axie. You can do it in a general measure space, where you have your measures, which are the activities, and you can have a map into the measures which correspond. So these are the activities, these are the densities, and you can invert in exactly the same way I did for the homogeneous case in that. But a key point is that there is a nice relationship with 3 structures. And if you ask me the questions, I will tell you. And we addressed that in a special combinatorial paper in Annal of Institut Arimpo Ankara in 2021, again with Kuna and Jansen. So this has been published, you can find it there. So this is about the inversion. This is one technical. And the last, and I conclude with that, is the relation with the large deviation principle, relation with large deviations. And the interesting thing is the following. So the large deviations, we work on the duality of measures, sign measures, and bounded continuous functions. But we found, so for example, start with rho, which is maybe almost sure continuous and infinity. So it can be a measure, so it is nicely here. But when I do the large deviation variational principle, the supremum is over Q, which are bounded and continuous. So what happens is that this supremum is not realized in the function space where I do, because the inversion I did. So actually, the supremum occurs outside the space on which I work in large deviations, outside bounded and continuous functions. In fact, if I invert a normal sure continuous density, I will get a normal sure continuous activity. So it will be in a space similar to this one, which is exactly what this inversion tells me. But large deviations doesn't capture that. Of course, it's not a problem because you can compute the supremum and you find the same value. You find the free energy again, even though where the free energy is calculated is not an element of this space. Okay, but I find it an interesting thing in the relationship with large deviation. So maybe one can start thinking of large deviation principles, and I'm not aware if there are rigorous theories on that. Maybe there are, and I don't know the papers. Large deviations where you don't work on the whole topological vector space, but maybe you work in poles or something like that, because this problem is related to the fact that you need a topological vector space. So if you take one direction, you have to take also the minus direction, and this is exactly we cannot work in these larger spaces. And I thank you for your attention, and I stop.
Thank you very much. So are there questions for the speaker? Nicholas?
Dimitrios, coming back very at the beginning to also Jonathan's question, what kind of pair interaction potentials can you cover? For example, could you cover these thin film micromagnetics potentials that you probably remember from our time at Leipzig? So each spin would now be a little magnet and they interact in a non-local way with each other.
A local mean field. Yes.
Not really mean field, but I mean, there may be also singularity in there, like I think it's h1/2, h to the -1/2 norm or something like that.
V is in h minus.
Yes, V the h. I mean, some interaction kernel depending on the S, which has a singularity. Would that be possible?
So In the position.
No, in the magnetization.
In the magnetization.
Magnetization and position.
In the, yeah, so it's I mean, I have not thought about it because you know it's very detailed. So, but let me guess. So in the magnetization, I guess I need integrability. It doesn't need to be excluded volume. I mean, I have control for excluded volume. Okay, so all I said, I'm sure for the excluded volume. Now, if I don't have excluded volume, so you have some attraction, you mean? They want to be aligned. I think
they want to be aligned, but at the boundary of the specimen, for example, they want to be parallel or orthogonal to the boundary or something like that.
And you are in the continuum or in the lattice?
Okay, in a continuum, probably the only thing that would happen is, unless you put in, of course, some external field that forces them to be in different regions to be different, they would probably like to be aligned. But say you force them to be different, in which way do they make the transition? Maybe they don't want to make this interaction prevents them from making the transition in a certain way, like in micromagnetics.
No, that's definitely one thing to study. No, we have not entered into that detail. So our work so far was on the estimates we need not from cluster expansion. Now, which cases this can cover in the orientation we have not seen, and it's maybe a next work, because what's the point? The point is that we want to specialize on liquid crystals, where now you don't have essentially special structure. No, it's almost homogeneous in the special structure, and you are interested in transitions on the orientation. Because in the cluster, in the liquid crystal, you have two kinds of phase transitions. One where the space is homogeneous, no, and you see oriented and not oriented, and another one where also it can create layers of also special structures. So we are yes on the orientation, and unfortunately I cannot answer to your question at this moment.
Okay, so there's still a lot.
No, it's it's.
Thank you.
Work to come.
Any further questions for Dimitrios?
If nobody has another question, I would like to ask something else. I mean, the cluster expansion has the advantage that it's a convergence series. Do you see a way to use this for computing numerically large deviation rates functionals?
Yes, definitely. I mean, this is one of the points, because that's a very good point, because you see this integral is a high dimensional integral. This integral is a high dimensional integral. No, so it's impossible to do in numerics. So the cluster expansion, what manages to do is to write this as a power series, where the first term is just one integral, the second term is two integrals, the third term is three integrals. Integrals in the product space. So it's very low dimension. And then you can do Monte Carlo to compute the coefficients. Actually, yes, this is an ongoing research in chemistry. So, for example, in the standard hard sphere system, they have there are papers called the 9th and 10th virial coefficient. So there are numerical methods in order to compute the 9th, 10th, 11th. Yeah, so it's definitely a method which is helpful for numerics. Yes.
Thank you.
Further questions? If not, let's thank the speaker again for the nice talk, and let's move on to the informal discussion. See you all next week.